Now we are going to talk about how to implement regularization for logistic regression. Like for linear regression, logistic regression can also present overfitting if we fit it, for example, with a very high order polynomial features like this. So if we use this polynomial, just over here, this one, the perfect decision boundary will be something like this. So here G is the sigmoid function. As well known, a hypothesis is proposed, whose decision bound is a kind of complex and extremely contorsive function that really isn't such a great hypothesis for this training set, and more generally if we have logistic regression with a lot of features. Not necessarily polynomial ones, but just with a lot of features you can end up with this overfitting, this kind of overfitting. This is our cost function for logistic regression. So this is our cost function for logistic regression. So if we want to modify it to use regularization, we just like for the linear regression, we just add here the term, the lambda over m times theta j, and this is just for j going to parameters theta j going from 1 to n. So this is not this equation is not for j equals to 0. For equals to 0 is this one, and we don't apply here regularization. So this has the effect of penalizing the parameters theta 1, theta 2, and so on through n up to theta n. And if we do this, then it will have the effect that even though you are fitting a very high order polynomial with low parameters. So coming back to this one here, with this kind of alpha, we can have a kind of decision boundary like this. So it looks more reasonable for separating the positive and the negative examples. So we using regularization, even when we have a lot of features, the regularization can help to take care of the overfitting problems. So coming back here, I will just add this one. So this term, so for the implementation, the procedure is quite similar for the previous one for linear regression, but what we are going to do is write the update for theta 0 separately, like in linear regression, as we mentioned before. So the first line is the update theta 0, and a second line is the update to theta 1 up to theta n without 0. So all we need to do is quite similar to what we did for linear regression, which is actually just modifying this second update rule as follows. And once again, this looks identical of what we had for linear regression, but of course it's not the same algorithm as we had, because now the hypothesis is different using this. So in this case, h of theta of x is equal to 1 over 1 plus e to the minus theta t transpose times x. So this is not the same algorithm as regularized linear regression, because the hypothesis is different. It actually looks the same as what we had earlier. We are working out gradient descent for regularized linear regression. This equation is similar, but the hypothesis it's different. So, and of course this term can be seen as the partial derivative of j given theta j. I'm sorry, this one. Yeah. So this term here is the new partial derivative for respect of theta j of the new cost function j of theta. Here j of theta here is the cost function we defined on our previous slide that does use regularization. So that's a gradient descent for regularized linear regression.